next presentation, which is also the last one from Georg. The title of the presentation is Evaluating the Lottery Ticket Hypothesis to Sparsify Neural Networks for Time Series Classification. And Georg, you can go ahead.
Okay, thanks for the introduction. Do you see my screen?
Yes.
My slides? Okay, so yeah, then I'm just, as you said, Georg Schlake from the University of Hagen, and I'm glad to show you the results of our evaluation of the lottery ticket hypothesis in the field of time series classification. As we all know, deep learning models tend to become larger, deeper, and in many cases even over-parameterized. And as we also know, there is an increasing number of AutoML models and frameworks enabling users even without any expertise in the field of machine or even deep learning models. And these two trends made to the point where the main constraint in using deep learning techniques may shift from missing human expert knowledge to more hardware constraints in either model generation or inference. And for this reason, it is important to find small yet expressive deep learning models. One way to achieve this is via pruning and the lottery ticket hypothesis. So I will start with the main basics of pruning before I will explain the lottery ticket hypothesis, which is a central finding in this field in the last few years. Afterwards, I will explain on experiments to test whether this hypothesis also holds in the field of time series classification, and I will show you our conclusions from them. And as for the pruning basics, I will start with a short overview of pruning and then explain the major design questions when creating a pruning algorithm. So, the main idea of pruning is to reduce the complexity of a neural network by deleting unimportant or even unnecessary connections. This idea dates back to Lacan in 1989, but became more important after a rediscovery in the era of deep learning by Han et al. In 2015. So what actually is pruning? Pruning is done by deleting unnecessary connections after training before fine-tuning the network. And fine-tuning means to train the network again, but only for a small time to regenerate for the information lost when pruning the network. So suppose we have trained this neural network on the left side here, and then we want to prune it. So we have to identify the weights we want to prune, which are red in this slide. And in our case, these are all the weights with a magnitude less than 0.5. And now when we prune this network, we will retrain the network. So the remaining weights change to come up for the information lost. So we have got a much smaller network, and hopefully this has the same expressive power as the original network. So there are a few design questions you do when designing a pruning algorithm. One of these is whether you prune single connections or whole neurons. The former is called unstructured pruning and may lead to stronger compressions, while the latter is structured pruning and is more efficient in pruning and inference. As you can think, unstructured pruning, when you can delete every single connection in detail, it has much more choice to find the unnecessary ones and don't have collateral damage when there is a single important connection in a neuron. So this can lead to stronger compression. Another choice is local versus global pruning. In local pruning, every layer gets pruned by the same ratio, whilst in global pruning, the position of the weights in the network isn't taken into account by the pruning decision. This means local pruning may prevent layer collapse, which is when a whole layer is pruned. But on the other hand, global pruning in most cases loses less accuracy before this point happened, because just like in the last slide, in global pruning you have more choice which weight is actually unimportant, and obviously it can happen that one layer is more over-parameterized as another layer, and so this layer can get pruned more without any important loss in accuracy. So the most important choice is which weights you want to prune. So this figure is from a study by Zhu et al., which was made also in the context of the lottery ticket hypothesis, where these different pruning techniques were inspected. These plots show which weights get pruned depending on the evolution of the weights in the training. The x-axis resembled the value of the weights at the initialization, so the start of the training, while the y-axis resembled the weights after the training. The colored parts of the weights are not pruned, so for example, large final means the weights which have a high magnitude after training are kept, whilst large init means that the values which had a high initialization value, these weights are kept regardless of the training performance. But as you might think, large final is a much better solution and is widely accepted as a good pruning measure. But in most cases, it's called just magnitude pruning because you prune after the magnitude. And this showed also competitive results in this study by Zhu et al. The last question is whether you prune once or iterative. If you prune once, so single shot pruning, you delete all weights you want at the same time, whilst in iterative pruning, you only delete a smaller fraction of the weights before retraining the network, deleting another part of the weights, retraining, deleting, retraining, deleting. And so you do it until you reach your final compression. Whilst this lowers the loss of expressive power in the networks, it is obviously much slower as you have to train multiple times. So after we now talked about the basics of pruning, I will put this together and we'll have a look at the lottery ticket hypothesis. So this hypothesis was created by Frankel and Carbon in 2019 and a year later modified by Frankel, Jugaite, Roy and Carbon to be more robust. It says that small subnetworks of neural network exist and can, with the weights of an early training iteration, be trained in isolation to match or even exceed the performance of the original unpruned network. So actually the only information you need of the training of the full network is the selection of the small subnetwork. In practice, this means that instead of fine-tuning the network after pruning, the weights are rewound to the values of a very early training iteration, k, or even at the initialization values. And this resulting combination of subnetwork and rewind weights is called a lottery ticket. And the algorithm to find these networks is called iterative magnitude pruning. And as well as iterative and magnitude pruning, like it says, it also uses global and unstructured pruning. These findings were made in the field of image classification and later also tested in natural language processing and reinforcement learning. And we want to show whether these findings also hold in the field of time series classification. So after we know the lottery ticket hypothesis, I will show you the experiments in which we tried to show that this hypothesis also holds in the field of time series classification. I repeat myself. So I will show you which datasets we used and which deep learning architectures. Then we will come to our final experimental setup, and last but obviously not least, the results of this. We used 14 different datasets for the univariate time series classification from the UCR time series classification archive, which was also mentioned in the last presentation. Every dataset consists of 30 different trained test folds, which were all investigated in isolation. So we then selected the slow problems, from which we omitted the U-Wave gesture library or dataset. So we hopefully have 14 different datasets which take all important parts into contact. And then we've got 420 different folds and use the McFly framework to select a model for every single one of these folds. These models belong to 4 different families of state-of-the-art deep learning models, which are the CNN family, the RESON family, the deep convolution LSTM, and the inception time family. So we used an actual AutoML framework and had these many different models. Each of these 420 models got trained for 80 iterations and pruned 10 times by 50%, which is a rather high pruning ratio compared to the other literature. We reset the weights to those after iteration 0, which we called IMP, and we reset the weights also to iteration 1, and this time we called it IMPR in our experiments. So we actually did 2 different experiments per dataset. And as you can see in this table, the weights, the networks got really, really small because in the end, they were much less than 1% or even 1 promille of the weights remaining. So for the results, I will first show you the average accuracy over all models we used. On the y-axis, you can see the accuracy, and on the x-axis, the pruning level. So the leftmost point, pruning level 0, is the actual unpruned model, and every level to the right represents another 50% reduction of the weights. We also plotted the variance to which is this area around the plot. As you can see, the accuracy actually increases up to level 3 and 4, which resemble 12.5 and 6.75% of the weights remaining. Afterward, the accuracy is clearly falling, but even after 10 levels, so with 0.1% of the original weights, the average accuracy is still over 50%, which is relatively good considering there are almost no weights left. Obviously, it's much smaller than at the beginning, but with this high pruning ratio, this is expected. But to this point, we have just shown that the neural networks we used were over-parameterized and we can gain accuracy. So to show that the lottery ticket hypothesis also holds in the field, we have to identify whether the weights to which we rebound the networks are also important. Hence, we reinitialized every model and plotted the average accuracy per model family. The reinitialized versions use the same pruning mask as IMP model, but don't rewind the weights, but reinitialize those new. So this is the same network, but without the starting weights. And as these results show, the reinitialized version yield worse results. And this indicates that the lottery ticket hypothesis holds in this domain. What we also can see on this plot is that the different model families lose accuracy at different pruning levels. So the inception time models lose accuracy already at level 5, whilst the CNN models have almost no accuracy loss up to level 7, which resembles to under 1% or 0.8% to be precise of the original networks. And they still have a good accuracy, and this time it's really good. It's not they still have a good accuracy even at level 10 with these 0.1% of the original weight. These differences in the model architectures might be due to different levels of overparameterization of these models in the McFly framework. But now we have only looked at the accuracy. In this plot, we want to see which fraction of which model family reaches their maximum accuracy at which pruning level. So what we see is that some models also reach their level even at level 10, reach their maximum accuracy. And on the other hand, we also see that not even half of the models in any architectural family has their maximum accuracy when it is unpruned. So this means that over 50% of the models actually gain accuracy when we cut away half of the weights. And we have some high points here at level 3, 4, or 5 in different architectures, but this is just to show that it really gains important accuracy. But you often don't want to go for the full accuracy or the maximum model compression, but a compromise between this. And so we have looked at how many levels a model can be pruned before it loses more than 5% of its original accuracy. And we see that this is for the most families, even at level 7, which means 0.84% of the weights remaining. Over 70% of the models did not lose much predictive power. And even 50% of these the models of these architectures don't lose much expressivity with only 0.2% of the original weights at level 9. Again, the inception time family is a bit under the loses a bit earlier its power than the others, but this might also be due to different levels of over-parameterization in these AutoML models. So, as we have now seen the results, I will draw my conclusions or our conclusions from them. So, we have seen that the IMP algorithm finds lottery ticket in these different deep learning architectures for the time series classification task. Even when we decrease the model size, pruning with a lottery ticket hypothesis can still increase the accuracy of a model. And rewinding the weights to values of an early training iterations is a valuable part of this. When we look at these architectures generated by AutoML, you can see that some of these can be pruned to extreme levels and still have a good performance. So, and with this, I will draw the finish line of this presentation. I'd like to thank you for your attention, and feel free to ask me any questions.
Thank you, Georg, for the nice presentation. Do we have any questions from the audience? Oh, Rihan, go ahead, please.
So if I understand it in a simple way, basically you are saying the less is more.
Yes.
So, and your experiment result is really interesting. I want to know, how do you decide the threshold, or to say, how do you say when I should stop the pruning?
Excuse me, I didn't understand your question.
So basically, because you're pruning the parameters of this deep learning architecture, do you know when you should stop the pruning?
Well, you see, if you look at this plot, for example, that on some points the pruning gets less. So, for example, if you look here, most architectures start at 0.8%, and at some point they just fall below this. So, for example, if you look at this accuracy of the inception time architecture, it goes much down after level 5. So you have to make a compromise between how much you want, so it depends actually on your use case. If you want to have the best performance, you can just look how much you can prune before it starts to decline again. If you want to, for example, have a especially small model, I would look at when the accuracy either is below a certain threshold you want to have. So you can say, yeah, I'm totally fine with my model, which will be 95% accuracy in the original case, but we can live with 90%. If the model is much smaller, then you can say we will stop when it goes below this threshold. But this is up to the use case.
So then, for example, if I give you a lower bound of accuracy, can you tell me when to stop theoretically, or this is something can only be done through experiment?
This has to be done by experiment yet.
Okay.
I think there are ideas to look at this before experiment, but I think they haven't been tested in practice yet.
Okay, thank you.
You're welcome.
Thanks, Rihan. Paul, go ahead, please.
Yeah, thanks for the talk. Do you see this as something that you would want to integrate into something like a machine learning ops system? This sort of pruning?
In the optimal case, and sometime it will be, but at the moment, this means you have to train the model multiple times, and this is obviously very slow. So it could be a possible optional option, but at the moment, as you see, to get this maximum accuracy, if I have to train the model 5 or 6 times, that will multiply the training costs in regards of time and resources by 5 or 6, which obviously would be very expensive.
Okay, I have actually a question related to that. Georg, so about the AutoML, right? One thing that people discuss a lot is exactly the computational efficiency. It requires a lot of time and resource, right? So have you made any tests like how much exactly it needs, how much time it needs more if we want to reach, for example, level 5 or 6 pruning?
With the implementation I took, it actually was quite this 5 or 6 times the same. Also, with the implementation I took by Frankel et al., which is OpenLTH, or just by Frankel, I think, in PyTorch, the pruning was not very well implemented. So training the pruned network took the same time as training the unpruned network. And this is hardly dependent on the this is depending on the software and the hardware you use, because obviously most techniques are designed for training dense neural networks, and in a pruned sparse neural network, this isn't good optimized anymore. So at the moment, there is no real.
I see. I see. Yeah, one might assume, right, that training a pruned network will be easier or faster than training networks with more weights. So, do you think it's possible to make some improvement for that, like some more specialized training method?
Yeah, I think there is. So by more specialized training networks, there should at least be a method to make this faster. And I think I've read press news from NVIDIA that they are actually researching special hardware to train sparse neural networks. So maybe there will even be some help from the hardware side.
I see. I see. Thanks for sharing your thoughts.
Thanks. You're welcome.
If we do not have more questions, I think I can hand it over to Rihan.